Okay, question 29. It says write an exponential function in the form y equals a b raised to the x power. The points we are given are 0, 5, and 115. There are a couple of different ways to approach this problem. The first way is to realize that 0, 5 is our initial value because it is on the y-axis with the 0 and up 5, and that means that a automatically equals 5. And then also to realize from 0 to 1, if it's exponential and it's a multiplication pattern, 5 times what gives you 15? Well, that means that b has to be 3, and it's y equals 5 times 3 to the x power. Now the other way to do this is to use your calculator and to go in L1 and L2 and set it up as follows. L1, L2, and 0, 5, 1, 15. So we're going to go to Stat Edit, and we're going to type in 0 and 1 in L1 and 5 and 15 in L2. Alright, then we're going to go to Stat, Calc, and we're going to go all the way down to, I think it's 0. Let's see. Yep, 0 is xpreg, so we're going to pick 0. And because L1, L2 is the default, and there we get A is 5 and B is 3 also. Number 30, based on the patterns of change, which type of function best fits the data? Linear, quadratic, radical, exponential, or logarithmic? And then to write the function. Well, we'll call this A. For A, the x values are going up by 1, and we can see that here there's a multiplication pattern of 4. So that tells us that this one is going to be exponential. And because the multiplication pattern is 4, we know that B is 4. And if you would back up the pattern to find the y-intercept, to find the starting value, well, what times 4 gives you 4? Well, that would just be 1. So it's 1 times 4 to the x, or just 4 to the x. You could put those in L1 and L2 and do xpreg like we did for number 29. I just don't feel like typing all that in. Okay, we'll call this one B. X's are going up by 1s. Here we are adding 5 each time because it's an addition pattern. This is a linear function. Because it's linear and we are going up by 5, that means our slope, our m value, remember mx plus b, m is 5. And if we back up the pattern to 0, well, that means we're at 0, 10, so it's going to be 5x plus 10. We'll call this one C. For letter C, we notice immediately that there is a pattern not on... Uh-oh, my tablet is frozen. That's not good. We notice that... Hold on. Pause. Okay, now we have a working active slate. Sorry about that. For letter C, like I was saying, we have a pattern clearly on the x's, and it's a multiplication pattern here of times 2. Because we have a multiplication pattern, sometimes that would make us think exponential. But here, it's on the x values. That's the opposite, the inverse of what happens with an exponential, and that makes this a logarithm. Now, there's no way to do this on the calculator because it's a multiplication pattern of times 2. It's just log base 2 of x. We'll call this one letter D. Here, there's really no pattern going this way. What we see is that 0 squared is 0, 1 squared is 1, that these numbers on the f of x row are perfect squares. That makes this a quadratic. And our equation is going to be y equals x squared. It's pretty rare to see a quadratic that's just that perfect. The only way we would really know is to notice, like I said, that it's 1, 4, 9, 16 perfect square numbers. We'll call this one E. We have 0, 400, 1, 200. It looks like a decreasing pattern. It's not a subtraction pattern because this is down 200 and down 100. What it is that we're halving or multiplying by 1/2 each time. This is an exponential decay. Our A value is 400. And our b value is 1/2. That looks like y2. 1/2 to the x. All right, and the last one for 32, letter F. Here we've got, once again, we've got this weird pattern. Well, it's not a multiplication pattern on the x's. My first thought was maybe it was logarithmic, but it's not logarithmic. But then I noticed that I've got 4 matches with 2, 9 matches with 3, 16 matches with 4. What we have here is a radical function because what is the square root of 4? 2. What is the square root of 9? 3. So here we have y equals the square root of x. Number 21. The number of bacteria in a culture in a function is a function of the number of hours the culture has been growing. The initial number of bacteria present in the culture is 50. The number of bacteria in the culture for each hour is represented in the table below. A. Which type of function best models the data? Well, immediately I can see that this is an exponential function because we are multiplying each times 3. Again, you could put this in your calculator, but because it's exponential, I so cannot spell exponential. We'll just go with exp, period. And we'll all know that that means exponential. Because it's exponential, and we see 0 is paired up with 50, we know 50 is our a value. And because we know that we're multiplying by 3, we know 3 is our b value. So there's our function. That's the answer to A. Here's the answer to B. C. Predict how many bacteria there will be after 9 hours. So we're going to have 50 times 3 raised to the 9th power. 50 times 3 to the 9th. And there we go. Bacteria. Okay. Number 32. Match each equation to the graph. So, here we go. We've got 4 graphs, 4 equations. I immediately know that A is a growth function. So I can ignore choice 1, and I am left with the other 3. Oh, wow, we're at it. Choice 1 is decay. What's the only one that has a decay base? D. So D has to match with 1. Okay. I see that there is no constant out here for A, going back to A. So I know it has to have an asymptote at y equals 0. So I look at my choices, and I see that 2 and 4 have an asymptote of 0. See, because there's that blue dotted line. So it could be that one, or it could be this one. So what I'm going to do is I'm going to look. Here I have the point 0, 2. And here I have the point not 0, 2. So let's see if the point 0, 2, because I can see it real clearly on my graph. Let's see if that matches up. So we have 2 times 3 to the 0. Well, 3 to the 0 is just 1, and 2 times 1 is 2. That works. That means this matches up with graph 2. All right, B is 4 to the power of x plus 2. Now, there is nothing, no constant out here. So again, we have another asymptote at y equals 0, and that means it has to be 4. So now by process of elimination, I know that C matches with graph 3. Another way I know that C matches with graph 3 is that it has this constant here. It's an exponential function plus 2, which means it has an asymptote at y equals 2. And sure enough, graph 3 has an asymptote at y equals 2. Number 33, match the equation with the graph. Alright, so I've got some log functions, I've got some e functions. The first thing I'm going to remember is that a log function is the inverse of an exponential, so it's going to go. And e is an exponential. Remember, e is just 2.7 blah, 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 blah. We don't really care what it is, but that means anytime I have a base of an e, that's going to give me a growth function. So immediately I'm going to take a look at these e functions. Well, not always. E is growth, except I notice I'm looking at these exponents. I have x minus 3, I have negative x, and I have just x. This negative x makes me wonder, because when I have a negative exponent, what happens to the base? It switches. So this is really 1 over e to the x. So these two, a and c, these are going to be growth functions. But b is going to be a decay function. Now when I've done a little investigating, let's switch colors. Let's start matching. So b is decay. There's only one decay function here, and that's 3. So I know that b has to match with 3. Cross that off. I have 2 growth functions, 4 and 5. So I have to decide which one matches with a. A has this -3 here. 4 has an asymptote here at y equals -3. That means a matches with graph 4. And by process of elimination, c has to match with graph 5. Also, no asymptote, or no constant, asymptote of y equals 0. Alright, d and e. Remember, log functions are the inverse of an exponential function. Here, I have nothing being added, so I have no vertical asymptote of anything other than x equals 0. Here, I have a constant, so I have x equals -1. Remember, these are the inverse of an exponential. So on an exponential graph, a constant would be y equals. On a log function, it's going to be x equals. They're inverses. It's the opposite. So graph 2 has an asymptote at x equals 0. And graph 1, sure enough, has that asymptote at x equals -1.